in logistics resemble the graph structure, where a lot of nodes are communicating with other nodes. There are connections, sometimes the connections that are one direction, or sometimes the connections that are in both directions. So it's bidirectional network. We look at the picture here. We say, for example, we have vehicles that are connected to the stations and warehouses that are connected to the intermediate points. And we have routes, etc. The vehicles are associated to the routes. And if you want to model the whole thing, it's a network. It's a graph. A network is a graph. So there are the complex dependencies between the component of this graph, this network. Opening a facility at some location will imply a lot of different decisions at different places. Capacity on the fleet of transporters to be deployed. And this choice of which facilities to be open, which facilities to be closed, which facilities to be relocated, and how much capacity to be allocated to every part of that network have significant impact on the cost, on the performance, on the carbon emissions, and so on and so forth. So basically, in graph theory, we say we have a few nodes, and then we basically it's a tuple. It's V and E. Graph G is defined by V and E. V is a set of vertices, and E is a set of edges. So the edges and directed or undirected, and so on and so forth. So it's basically this is a simple example of how a graph would look like. So there are graph. When we talk about graph, we go in the context of combinatorial optimization, where we have a lot of different combination of points that can represent the solution of the problem. And for example, shortest path, we have different combination of intermediate points going from one origin to destination. So there could be multiple paths with the same optimal solution, the same or even with the same objective function. So the simple example of this combinatorial thing is the shortest path problem. We have several algorithms that are known, exact ones with the Dijkstra, the Bellman-Ford, and also some heuristics that are like A star is known to be very efficient in this case. So this is typical shortest path calculations, how we calculate the minimum distance from every node to the central node, to the origin, to node 0. And we this is relatively even if it's easy to calculate, I mean, when we go to the larger scale, this becomes very complicated and has to be dealt with in some ways. Sometimes it becomes so complicated that we need to do some heuristics or maybe some kind of aggregations or some sort of thing that imagine you have a lot of different cars in the city or the trucks that are deployed, and for every one of them need to solve this one, and for several time during the day, and this is really excessive. So what do we have to always do the things this way, or can we do it different way? Well, there is a concept in machine learning. It's called learning graph. I mean, in general, there is a concept. It's called learning graph representation. So the idea is to extract some sort of information from components of the graph and be able to reconstruct later. So, for example, node U here, it has a neighborhood. We need to be able to get an embedding of this node using an encoder. So we end up with an embedding ZU here. And this array, this vector of real numbers, we should be able to, one more time, to decode it, and we come back again to the same neighborhood structure of that given component. So this is basically the idea behind learning graph presentation. So from one graph, we end up with a few vectors, embeddings, and then these embeddings should have this property that if two nodes are neighbor here, they must be neighbor in the embedding space, and then we project it back again, and we decode it, they come back again together in the original space. This is the we use a lot of these kind of algorithms in node classification. If we have identified threats in the past, we have identified formation of certain type of cellules, kind of the threat cellules or this communication spots, we can identify them again using node classification, identifying possibly the faulty segment of the network. We can use it for link prediction, where we identify possible connection between for example, we have a client that has been ordering a certain type of product. We have another or several other clients that have similar behavior. When they order this set of products, they end up with ordering another one too. So maybe based on that, we can identify a possible order or possible connection between this client and the future and the other products that maybe it could be used to in the recommending systems, such as Netflix and others. We have on the knowledge graph, we use them on the recommendations. For example, when the social media recommend you to connect to someone, is basically because this potential has been identified through this sort of structures, through this graph representation there. So the challenge is that we in the learning normally, in the machine learning normally, we often in the past we were really, or even now in many models, they stick to the specific size and the specific structure. So once they are trained on that structure, they stick to that one, and if you providing them with the input, it's like distribution shift, and this will not deliver the right result. So what we are dealing with the irregular structures in the graphs. A graph, if we in the 3-dimension, if we rotate part of the graph, it's still the same graph, but if we feed it into a normal neural network, the result will be totally different. It might be totally different. The distances are non-Euclidean, and the correlations are very complex. So what is the solution? The solution is to be able to project this graph into the space of the embeddings in Rn, Rm, or X, and then be able to bring them back again. So do the studies, do the learning on that space, a space of the vectors, and then bring them back again to the output to the original space. So so this is basically the idea. We have graph neural network. Is that instead of input in this kind of giving the graph directly, we transform the graph into embeddings. So how these embeddings, how the things work in graph convolutional network? The idea is a combination of convolution and the graph thing. In convolution, we had a big picture. There was a cat at some part in the picture. So we train the network on identifying cats, and then you give them a big picture, a larger scale image, and say, okay, find the cat. Is the cat inside this image or not? And you will be able to, by moving a box, moving a convolution around this the image, will be identified, say, yes, there is a cat, and that's located there. So if we bring this one into the graph structure, then by neighborhood aggregation, so collecting information from the immediate neighbors, and kind of evolving this and doing this for all the nodes, we can create some sort of message passing where after a certain number of layers, the nodes will be aware of, one node will be aware of all the nth neighbors of the associated to it. So these are the sort of networks that are independent. GCNs are sort of networks that are independent of the size and are independence of the order of the nodes being supplied to them, being fit into them, and they are able to capture these dependencies very successfully. So the presentation must assure that the structure will be preserved, the features will be learned, and we also need to be compatible with the machine learning paradigm. We look at this picture here. This is that we have the mosaic graph, and this is the features, and these are the features that are partially missing. I mean, sometimes there are new nodes appearing in the network for which we do not have the information. We do, but they will be calculated over the time. So the important components are the message passing, is that every node is aware of itself and also aware of the neighboring nodes, immediate nodes. So if we add one more layer, it will be also aware of the nodes in the second neighborhood with the radius 2. If we add one more layer of network, it will be aware of the third, and so on and so forth. So we do message passing. We send our information to the others, and we can receive information from the others. We do aggregation. We collect this information. We add it to our own information. We make an average. We update this way, and then we iterate. We do that over the time. After n iteration, we will be able to have information from the nth neighbor in the network. This sort of this is an area where there's a lot of new application emerging in identifying new molecules, new drugs, new sort of combination of identifying the molecules that have certain level of certain temperature for boiling temperature. They smell the same, or this kind of threats that can be kind of identified through this, be learned through this machine sort of network. The key advantage is that these are also the result sort of network that are interpretable. So basically, we will be able to explain what happened. So all said, our problem is not a logistic problem. It's a problem of we have a depot, we have a set of nodes, we are leaving depot by truck, by a set of trucks with capacity, and we need to visit customers at different locations, deliver packages, and maybe within a time interval, or maybe not, very just capacity. And we have to return. So how we identify a route for every truck? Of course, the idea is to reduce the number of to minimize the number of trucks being used, and also the time, the trouble cost. So the mathematical formulation for this is here. Well, it is very challenging, very challenging problem, even for a very toy-sized problem. Toy-sized instances it's not really. I mean, it's hard to imagine that can be solved to optimality or to any feasible solution within a short period of time. Therefore, we need to have an alternative. Most of the solutions being deployed in industry are heuristics, and which are good, but there is no guarantee of optimality. So the idea is whether we can do this with the machine learning, with the graph machine learning, or not. So we have. So what the challenges are? The computational complexity, the struggle to incorporate real. I mean, even the model in the simplest form is complex, is computationally challenging, but it's integrating real features such as, I don't know, the constraint on the driver, constraint on the emission, and so on. It becomes even more complicated. It's not imaginable how to solve these things. Even when we devise a solution method, the solution method needs to be fine-tuned to work on certain instances, and then when we apply to the others, the performance is bad. And if we, for some reason, we have during the day, we need to replan the things and some kind of unforeseen event, then this becomes complicated because we do not have enough time or enough resources to do recalculation. So basically re-optimize the whole thing given the disruption or whatever. So the idea is to to learn this routing strategy. Maybe in the past we have had the we have historical data. We have we know that when the load is there, has this specification, what kind of routes has to be designed, and which kind of truck has to be assigned to that road, to the route, and so on and so forth. And then when we train this system, which delivers solutions with good quality, but probably not optimal, but with good quality, then it will, if whatever happens during the day, if the solution becomes infeasible or becomes due to some unforeseen thing or disruption, we can quickly do another inference and get it kind of dynamically get another solution. So what we have done is that we have a layer of we have devised a layer for VRP. Basically, this is the very, very basic level that can be a layer that can be used, is that the features are the coordinates and distance to every other node in the network. We also have the adjacency matrix and also the identity matrix where the self loop is happening. So degree matrix and normalization of this, which we then end up with a tilde. And then this has to be updated during the truth-sum convolution. The convolutional layer is applying the sigma function, or the kind of activation function on this one, and then we have some inferences afterwards. So the sigma is often the ReLU, is this function that is being used. And every time the HL plus 1 is HL plus some information that is being collected from the neighbors. The update formula looks like this. So HL plus 1 is equal to the ReLU of the previous one, and then it follows by a decoder. So we had a encoder layer, this layer, and then a decoder layer, which in the end identifies the routes that are constructed, and based on the volume that is going to be deployed on those sequences, we can identify what kind of truck to be deployed on those kind of routes. So the side product will be also able to enhance the demand forecasting. So when we have the historical data, we can use that one as a side product to identify the forecast to the demand pattern, which is then also influences the decision on the identifying routes. The route optimization becomes intelligent, but we don't have to do everything again from the scratch. So we pick up from where we left last time. And these kind of networks are very capable to identify the dependency, the inherent dependency within the elements of the network. whether this is depot or the interrelation between the clients and so on. So we had this we had this some initial experiments on some real data. This can reduce the cost significantly. In particular, can also contribute in delivery time and also in forecasting. And this way, given that the distribution, the data distribution moves very kind of continuously along time, we will be able to have the model that are reliable and the predictions that are that can be trusted. Yeah, so the solution we have developed is this one. And this is a toy example to show how it works. So basically, we have a depot which is somewhere close to London, and then we have the 3 routes here being this is a capacitive vehicle routing problem. We have in total we have 14 nodes. We have one route that is only composed of node number 13, a route that is composed of 2, 3, 4, and 5, and another route that is much longer. So this is the output. Yeah. So basically that's it. Thank you very much for this opportunity.